Hello. Hello, everyone. Thanks for coming. Um, it's great to see you all here. Welcome to the Robotics seminar, the one from the last this semester. Um, it's an honor to introduce Yuval Tassa, who is coming from DeepMind, where he's a research scientist leading the robotics simulation team. And with that comes leading the development and maintenance of MuJoCo, which many of you might know. Maintenance, which sort of took on a special toll since about a year ago, a bit more than a year ago, when DeepMind decided to acquire MuJoCo and open source it. So Yuval has been involved in the development of MuJoCo for much longer than that. He got his PhD in 2010 from in neuroscience from the Hebrew University, and right after that, he spent 4 years with Emo Todorov at University of Washington doing his postdoc, a time which I can only guess that was intense and interesting, and which he did influential work in model-based control, but maybe one of the most influential things that he did there was sort of contributing to the development of MuJoCo, something that sort of has become an important computational backbone for a lot of research in robotics today. In many areas, including, for example, important to DeepMind, deep reinforcement learning, which I don't think that's what he comes to talk about, but maybe, who knows. So for those of you who have had the chance to meet Yuval or hear him giving a talk, you might know that he's a very enthusiastic and brave and honest speaker. So we're up for a good time today. And one of the things that comes with that bravery is that he promised that he will not just explain us what he's been up to recently, but he will also give a live demo. So we're going to hold you on to that. One last thing before giving you the mic is that we have another guest today, Taylor, who is accompanying Yuval, and he is a PhD student from Stanford who has actually spent recently some time at DeepMind with Yuval and has been doing important contributions to, I believe, some of the work that you're presenting today. So thank you. Welcome, both of you. Thanks for making the trip, making the time. We're going to all be looking forward to that demo.
Thank you so much, Alberto. I think I'm mic'd up. I believe I am. Thank you so much for coming. Hello, CSAIL. So after that intro, I think I'll do a little bit of my own intro. So I want to tell you a little bit about MuJoCo origins quickly before we get to the main bit of the talk, so you'll see a bit where I'm coming from. So MuJoCo was created by Emo with a little bit of help from Tom and me. Tom is my partner in crime. We've been working together for almost 20 years. And as you can see from the name of the paper, where it was presented in exactly 10 years ago, sorry, MuJoCo is designed for model-based control. And I'm going to go deeper into this in a bit, but I'll say a few words very general about model-based control. It's very powerful and robust, and it's quite fast. To the degree that it can work in real time and is kind of very compatible with human intuition timescales, and I'll contrast that in a bit. It has some disadvantages. The biggest disadvantage, which I'm going to address today, is that often the results of model-based control are difficult to understand and difficult to reproduce, mainly because you need to understand trajectory optimization, for which you need to understand optimization, for which you need to understand calculus, and you probably also need to understand floating point precision. And there's just so many things that you need to understand. And I don't think you need to understand all that. I think you can do model-based optimization without understanding any of this. There's also some other disadvantages, which I'm going to talk about later. Of course, you can only control what you can model, and you need an estimator. These are all things we'll get into. Very, very quickly, I'll show you like maybe a small clip out of this. Let me scroll forward to the best bit. So this is what you can do. This is real-time screen capture on the 2012 laptop using an algorithm called ILQG. And we're going to talk about that a bit more later, but the video is cool. So in 2014, Tom and I left Emo's lab, and we joined DeepMind. And we showed that video that I just showed you. And we thought, or at least I thought, everybody is going to want to do model-based control, right? It's pretty easy, and you get these beautiful results. Everybody's going to do this soon. But we got to DeepMind, and DeepMind were really into neural networks. And they had some beautiful results in discrete. Then it was Atari. They had solved a bunch of Atari games. This is a discrete rather than continuous environment in terms of the actions. And there was a young man there called Tim Lillicrap. And he kept saying, let's try to do RL for continuous control. And whenever he said this, I would always tell him, it's never going to work. It's never going to work. But he kept bugging me. And in the end, he won. And we tried, and it worked. And it worked beautifully. And this is like an example of, these are all tasks solved with RL. And RL is, in general, machine learning is a beautiful, beautiful thing. You don't need a model. It learns its own model. You can incorporate multiple sources of data. It's kind of fundamentally easy to understand this idea of reinforcement. It's easy to use. It has all these advantages. But it has one, as far as I'm concerned, huge disadvantage. And that is that it's slow. Learning is slow. You hit enter, and if you're lucky, you get something by the time you get back from lunch. Usually, you need to wait until tomorrow or maybe next week until something happens. And that, to me, that for my brain, it's unacceptable. I need to click a button, and something needs to happen instantaneously. That's how I learn. OK, so I'm going to switch back again to MuJoCo and talk a little bit about model-based control. And in the end, I'll get back to learning and talk to you about how we can try to combine these two things. So I'm not at all going to talk about this slide about what makes MuJoCo a great physics simulator. I just want it here so that in the future, people can pause the video and read the slide. And now I'm going to move on to the next slide. MuJoCo has great documentation. Very important, as of June of 2022, MuJoCo is open source. And it's not a code dump open source. This is real open source. We accept pull requests. We are updating it. We answer questions. We have an exciting roadmap that maybe at question time I'll talk about a little bit. But MuJoCo is a rare, true open source community project that we are very, very proud to lead. Let me show you this video. This is an example of, we have a library of curated robot models, which we're going to make much better by doing proper system identification on all of these robots. It's called the MuJoCo Menagerie. Oh, what happened there? MuJoCo is also very fast. Now, it's interesting to say because MuJoCo doesn't have a reputation for being very fast, but unfortunately, I have to take the blame for that. This is entirely our fault. The reason is that the way most people approach MuJoCo in the last 5 years is via Python. And Python kind of kills threading. Python is incompatible because of something called the global interpreter lock. You cannot have really efficient multi-threading under Python. But if you don't use Python, you can get, for example, on a good CPU like a Threadripper, 1.6 million steps per second on a humanoid. And by the way, when we measure the humanoid, it's not static. We inject noise into the actuators, so the physics cannot warm start. So we can simulate this 8,000 times faster than real time. It's very fast, as long as you don't use Python. And finally, MuJoCo has a few very important control-related features, which we're going to exploit in the work I'm going to talk about. The important ones are that the state is well-defined. So you can, for example, finite difference with respect to it in a well-defined way. It's very much principled. There are no hacks. It's just plain physics. And I'm not going to get into the details of the smooth contact model and inverse dynamics, but suffice it to say that you can do things. So for example, this is an LQR controller balancing through contact. And we have a Colab example on the website, and you can see how this works. It's surprisingly easy. And one of the maybe least appreciated features of MuJoCo, but I think incredibly important, is that it has interactive visualization with native rendering and user interface, which means that you as a researcher can write your own application very easily. And the example I'm going to talk about today, it's the focus of this talk, is a tool called MuJoCo MPC or MJPC. It was written by Taylor, who's sitting right here, during his summer internship. And it's basically, well, I'll show you in a second what it can do. So an important thing to say, Taylor is an incredibly talented guy, and if you're hiring, he's in the market. I'm going to try and hire him, I'll tell you that. But even though he's very talented, it's not like he came to us with this deep experience of MuJoCo. He knew MuJoCo superficially, but he never looked at the API very carefully. And within 3 months, he was able to write this tool. And what MJPC is, it's basically a tool for simple finite horizon predictive control. I'm going to show you examples very quickly. The main features, I'll go through all of these, is that the simulation and planning are asynchronous. This is an incredibly important thing, which I'll show you in a bit how and why it's important. Everything is exposed in the GUI and can be changed in real time. We currently support 3 shooting methods, but in principle, you could add direct methods or any other kind of method that you like. We have this cute implementation of risk sensitivity. And of course, the most important thing is that it's fully open source. So what is the problem that MJPC solves? It's the very simple finite horizon, or rather receding horizon optimization problem. Right? We have discrete classical, discrete time dynamics. We have some running cost. And the thing that we want to optimize is the cost from the current time until some fixed horizon t. Very simple, right? This is predictive control in kind of algorithm form. It's a very trivial thing once you get used to it. You have 2 things happening at the same time, completely asynchronously. There is the agent. The only thing that the agent does is read out actions from the nominal policy. Usually the policy is some time-indexed open loop thing. Doesn't have to be open loop, but think of it for the moment as some open loop trajectory. The agent just reads out actions. The planner, whenever it wakes up, it grabs the state. It either reads it or estimates it, depending on the setup. And using whatever nominal it currently has, it takes 1 step. Well, I take 1 step. We'll talk about it later, of some optimization procedure and updates the nominal. That's all there is to it. I'll talk a little bit about the cost structure that we picked and how it's related, why it fits well with MuJoCo. The cost structure, the base cost, this L that you see at the top, is just a sum of weighted terms. So W is some non-negative number. The norm function takes in a vector and returns a scalar. It gets it 0 at 0. So this thing is small when the r's are small. And what are the r's? We call these the residuals. It's basically vectors that you want to drive to 0, element-wise. The residuals are implemented as MuJoCo sensors, which you'll see in a second is incredibly easy to do. What is a MuJoCo sensor? It's a vector of values that get computed at every step. Why is this valuable? Because MuJoCo's finite differencing function for derivatives, which is already efficient because it doesn't, so for example, when you finite difference with respect to controls, it does not recompute quantities that depend on position and velocity, etc. So it's already an efficient function. But the important thing is that finite differencing scales like the inputs, right? It scales like x and u. So if I add more outputs, I get their Jacobians for free. So finite differencing is good. So you get exact first order gradients and you get Gauss-Newton Hessians. We also have this implementation of risk. I'm not going to go into it very deeply, but I'll explain it a little bit. So the classic risk-averse formulation uses an exponent with an exponent with a positive coefficient. And this means that high-cost values become worse. And there's some beauty there. You can solve it analytically in the linear quadratic case, and you get classic risk aversion. But what is this negative coefficient, these blue lines? Well, it's actually quite interesting. So think about a quadratic. Let's say that L is a quadratic, and R is -1. What do we get? We get an inverted Gaussian. So we would be, right, we would be minimizing something like 1 minus a Gaussian. So we get an interesting parallel between the rewards of reinforcement learning, right? So generally in RL, people use bounded rewards and they maximize them. Usually some number between 0 and 1 that you try to maximize. If we think about this number as an exponent of something, right, negative exponent, then we see that these rewards are actually risk-seeking. So by bounding your cost between two values, you get basically a risk-seeking cost. And we can talk about this more in the questions. We didn't explore this very deeply in the paper, but I think it's really worth looking into. So let me show you what setting up a task in MJPC looks like. So in my XML, I have these lines. This is a cart pole task. So I'm basically saying I have a numeric value called a goal. By default, its value is 0. And give me a slider to change it between -1.5 and 0.5. And then I have 4 terms. Remember those terms in my cost L, those sum? Give me 4 of them. One is called vertical, centered, velocity, and control. And there on the side are the numbers that define the initial values of the weights and the values of the sliders in the GUI, and a few other things that I won't get into. And then I just need to write literally 4 lines of C code. I'm saying vertical means I want the cosine of my angle to be -1. Okay, I want to drive all of these to 0. Centered means I want to have the position of the cart to be this parameter that I just defined in the GUI. And bring the velocity of the rotation to 0, and bring the control that I apply to the cart also to 0. That's all you need to do. And what you get is something like this. So here I'm turning on the planner. Takes it a while to figure out what to do, and it's like, oh, if I do this, I can balance, yeah. And now everything is available to me. And of course, I'll show you this in the demo. All right, so I can change. Now I'm turning off all the cost weights, and it just falls down. Changing the goal does nothing now. Let's turn on the centered cost. It takes the center. Turn on the vertical cost. It balances. OK? Very, very simple. We have 3 shooting methods. Let me show you them in sequence here again. There's ILQG, which is AKA ILQR, which is a classic second order or 1.5 order, people would say, shooting method. It's like a Gauss-Newton approximation to DDP. We have gradient-based. This is basically Pontryagин's maximum principle, forward, backward, classic. And we have something we call predictive sampling, which is a very fancy name for random sampling with a fixed distribution. It's a very trivial thing that I'm going to spend a surprising amount of time talking about, despite it being so trivial. In fact, because it is so trivial. Let me show you this asynchronous slowdown, because this is incredibly valuable. So look at this quadruped. It's trying to get over the hill, but it can't. So I'm slowing down the simulation. See, I'm now at 66% real time. Let's play that again. I'm slowing down the simulation, which effectively gives the planner more time to think. I'm making the planner faster with respect to sim time. And this means that it kind of doesn't matter if I have a slow machine. I can just slow down the simulation, and the planner can update more frequently, and I get nicer behavior. So I can use this tool on any machine. And what I'm hoping is that this would lead to, call it a democratization of predictive control, because I want everybody to be able to play with this tool. And one last thing before we talk about the predictive sampling, and I show you the video, is the spline representation. So if you're doing something like ILQG, you kind of are forced to use the discrete time representation of actions because of the Bellman principle, right? The future cannot affect the past. But if you're doing something like gradient descent or sampling methods, you can compress your action sequence very efficiently. You can do it in multiple ways, and we picked the simplest one, which is just spline. So instead of optimizing the open loop control sequence, we just optimize these knots or control points of the splines, and this compresses the search space dramatically. And of course, because splines are linear, the values are linear in the control points, we can push the gradients back in the gradient descent case very, very easily. And this turned out to be quite valuable. So before I talk about predictive sampling, I'm going to show you a video summary of this tool. And I hope you like it. So turning the controller on, it stands up. And now I can just change the speed goal. And it starts. Here I'm visualizing the prediction. So here you see the predicted positions of the center of mass. I reset it and it stops, like turn off these annoying traces. And now I make it walk again, but I can perturb it. So everything is completely interactive. Everything happens in real time. Look, I changed the height. It does this funny walk. Here I'm showing you different planners. This is ILQG solving this swimmer task. Here is predictive sampling, gradient descent. And here's a humanoid. Much higher degrees of freedom. Still works very nicely. Let's let it figure out. Standing up, turn the controller off, it falls down. Turn it on, takes a while to think, and then stands up. And you can perturb it. How do I stand up? Like this. I can change the height goal. So the availability to the GUI of all the knobs is one of the most powerful things here. So here's a quadruped with a very, very trivial cost. Look how robust this thing is. It's very difficult to make it fall on its back. Here is the thing I showed you a clip from before. Notice we can have goal transitions, so when you reach some, when some constraint is met, we can switch the goal. And now I'm slowing down the simulation, and it manages to climb over because it has enough time to think. And finally, I'm going to show you some, this will be more fun when it's live in a few minutes. Here's in-hand reorientation of a pretty high degree of freedom hand. Like, this is generally considered a pretty challenging task. And we're basically effectively using the noise to sample, to smooth over the difficult bits. So what is this predictive sampling thing? I'm not going to call it, it's not novel, and it's not even good. It's bad by design. It's the simplest possible sampling-based shooting method. Literally roll out n samples. Well, you roll out your nominal, and another n minus 1 samples with a fixed distribution, Gaussian. Pick the best one, that's the new nominal. This is the algorithm. It's not an algorithm. It's literally the simplest possible thing that you can do. And it works kind of well. Its value is not that it's clever or that it's good, is that it's simple to understand. We made a pedagogical Python notebook, which you can find on GitHub. And anyone can understand how this works. It's so trivial. So the big question here is, how can something that is really this trivial be kind of competitive with proper optimization methods, right? ILQG kind of takes a Newton step. How could random sampling possibly compete with something that does something so clever as taking a Newton step? Well, there's two answers, and they're both interesting. The first one is not so interesting, and I also think it's not the right answer. This answer is that sampling is just fast, right? When you need to do ILQG, you need to first roll out the nominal. Then you need to compute derivatives, which take a long time. Then you need to do the backward pass. Then you need to do a line search. And all of these things take, this is for the humanoid, help me add this up, 25 milliseconds. If all you're doing is rollouts, it takes 3 milliseconds. So you're like 8 times faster. OK, so you're 8 times faster. Can that explain this competitiveness? I don't think it can explain it, and I think the explanation is much more subtle and much more interesting. And the answer is that predictive control is not optimization. It is inherently, fundamentally different. Optimization is about finding the minimum, right? We all know this. Optimize, find the minimum. Find the gradient, find the Hessian. Do whatever you need, find the minimum. But predictive control is different because the optimization landscape is constantly shifting. By definition, the optimization landscape is shifting, and it makes the problem different. Good example, it never makes sense to converge when you're doing predictive control. You took one step. I don't care how you took the step, Newton step, gradient step. You took a step. You should never, or unless you've got really good reason, you probably should not take another step. Why? Because time has moved on. You've spent some time making this optimization step. The world hasn't waited for you. The robots moved. Things have changed. Go grab the new state. You're working on an outdated problem. So convergence is the wrong criterion. We're not trying to find the minimum. What we're trying to do is to stay in the basin of attraction of the minimum. The minimum is getting away from us. And we're on the side of the basin of attraction trying to get to it. So we're not doing mountain climbing. We're surfing. Do you see the metaphor? The basin of attraction is moving, and all we need to do is stay in, well, the minimum is moving, and all we need to do is stay in the basin of attraction. Sorry?
You still have to find the way to start. There's a potentially hard problem to even get in the vicinity of a good solution.
Oh, you're saying, how do I even get into the basin of attraction? Yes? Yes, 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 of course. But it's about how to think about the problem that's being solved. It's about what are the emphasis. Yeah, of course, a better step would be better than a less better, a less good step. But it's about what you emphasize, where your emphasis is. And my point is that convergence towards the minimum, if it's linear or quadratic or whatever, I don't care. It doesn't matter. OK, so let's talk about what you can do with this now and what you can do with this in principle, and how much time. Oh, good, I have time. So the first thing you can do with this now is just task design. Right? If you're designing some task that maybe you're solving with a completely different method, you should probably use this tool to design your cost, because it's so much fun, and it's so easy. And once you have your cost, go take it somewhere else. And you can use it to generate data. If you're doing RL today and you need data, this is a great tool to generate data. Either offline, generate a big pile of data, call it expert data, or online and call it a sort of expert exploration. Why would you explore with Gaussian noise when you can explore with this? So much better. So you can think of this, or at least of predictive sampling, as Gaussian noise that's been selected. Choosing between this sample and that sample of Gaussian noise. Of course, if what you're about is predictive control, then this is a great platform to do predictive control research. And in particular, this is a good platform because it has this super trivial, silly even, predictive sampling algorithm, because this is a baseline. If you cannot do better than predictive sampling, then you're doing something wrong, because it is literally the simplest and in some senses worst thing that you can do. And of course, this whole thing is just a code sample. You want to do something else? Use this as a code sample to make your own rich graphical user interface application for whatever task you're solving. So, of course, MJPC can only control what MuJoCo can simulate. And that's a general limitation of predictive control. There are a lot of really interesting directions in what people sometimes call model-based reinforcement learning, where people try to learn the dynamics. And I think that for lots of cases, this is exactly what you need to do. You're never going to get a traditional simulator simulating, I don't know, fabric or fluids much faster than real time. But maybe you could learn that simulator. I mean, certainly, it feels like our brains have built-in simulators that can predict the overall behavior of a fluid without simulating each molecule. So this is possible. I would say if that's what you're doing, have a standard simulator as a fallback so that you can disambiguate. So I would still say plug in your learned dynamic model into MJPC so that you can compare and disambiguate between modeling errors and other kinds of errors. And of course, you don't have to use MuJoCo. If you have a different simulator that's better at different things, use other things. which we applaud. So let's talk about the real limitation of predictive control. Predictive control is myopic. By definition, it's myopic. If all you're doing is optimizing a finite horizon, you cannot see past that horizon. A very easy and I think very attractive thing to do is to do exactly what I was just showing you while learning a policy. And the reason it's attractive is that it can only improve performance. So when you're rolling out your samples, and I don't care how you came about the other samples, maybe they're doing predictive samplings, maybe they're line search from gradient descent, also roll out your learned policy. If your learned policy is better, that's the new nominal. Okay, so you can have a constantly improving thing, and I think that's an attractive proposition for any algorithm. The second one, of course, is value functions. We all understand this. If you terminate the finite horizon with the infinite horizon, probably discounted or average cost to go value function, you can see into the future. And this is what a lot of breakthroughs were based on. For example, AlphaGo. I would love to see an AlphaGo for control, where you have a kind of model-based search that's informed by a learned policy for a short horizon, and then terminated and bootstrapped with a learned value function that can see into the future. And I think we can do beautiful things with this approach. But the approach that I'm really most excited about is the hierarchical approach. And in a sense, roboticists have been doing this for ages in a very limited sense, right? This is what you see Boston Dynamics do, and et cetera, right? You have a low-level controller that's in some senses stupid, and on top of it, you have a high-level controller that's more intelligent but slower, or something like this. And I think the low-level controller should be a very myopic predictive controller. And then on top of it, you have maybe a learned agent, maybe something that works in a different way, that communicates with the predictive controller by using the semantics of setting the cost function. Right? So instead of having to send this torque to this motor, and this torque to that motor, and this torque to that motor, you just say, put the hand here. And the low-level predictive controller takes care of that. And this gives you a separation between, this is very similar, by the way, to the spinal cord motor cortex separation, or also levels of the motor cortex. Like, you can see some of this hierarchy in biological systems. But this is something that I am very excited about, and I hope to be trying soon. And finally, the big question. Let's talk about hardware. So I assume that everybody in this room wants to see robots do amazing things. I also want to see robots do amazing things. But before I tell you how I think we can do that, I'm going to take a devil's advocate position and tell you why I think we shouldn't. And the reason is that we're not ready. Because hardware is hard. Anybody here that has ever worked with robotics hardware can tell you that hardware is damn hard. Simulation is always easier, yet we haven't solved the hard problems even in simulation. And when I say the hard problems, I mean the motor control that you can see a 5-year-old do, right? Or a 1-year-old chimpanzee, or a 3-month-old squirrel. Let's solve the hard problems in simulation first. Let's see a simulated robot, opening and closing a bottle cap, or using a pen, or I don't want to say tying shoelaces because that's really very hard, but think about the things that you help a 4 or 5-year-old learn. doing with their hands. That's all what they care about, is how do I use these hands to do stuff. Show me a simulated robot that can do it, and then let's take it to hardware. Then let's ask, how do I transfer this? Now that I've said this, there are lots of big problems with this argument. The main one is that when you do things in simulation, you can cheat, and I realize this, and it is important to have hardware. So let's talk about hardware. So the first answer, which I've already given you, is transfer learning. People have been working on this for a long time, right? You learn something in simulation, you collect data, you transfer it to the robot. We can do this, maybe. It doesn't work so well, but it's at least worth a try. But of course, the real answer to controlling hardware is to just have good estimators. And I say just, it's not just. Writing good estimators is hard. It's a hard problem. I think it's solvable. I'm not exactly sure how to do it. I have some directions which I want to try. But I'll tell you one thing that I'm certain of. The good estimators that we need to write to estimate things, multi-contact situations with occlusion, where you can't really see what's going on. Is the robot holding the thing? Is it not holding the thing? Is there force? Is there not force? The only way to get a good estimator is to have a responsive GUI application where I have a screen next to the robot, and I can look at the robot, and I can look at the screen, and I can see the estimate, and I can see the robot, and I can tweak all of the knobs, and I see, there's a problem with this knob in my algorithm. If I turn it up, the thing bounces up. I get a bad estimate. That's the way to understand your algorithm. Whatever the algorithm is, if you have a reactive, responsive GUI application that you wrote and you understand, that's how you really learn how to understand your algorithm. So I'll give you a summary, and then we'll get to the moment you've all been waiting for. So MJPC is an open source interactive tool for predictive control using MuJoCo, written by Taylor Howell in 2.5 months. And the main point of this talk is not to introduce something new and better. It's about lowering the barriers to entry. It's about making predictive control accessible. It's about giving you and everybody else easy-to-use open source tooling and introducing, branding, sampling from a Gaussian with a name, which we call predictive sampling, because I think it's important to have something that's really easy to understand, that anyone can play with and conceptualize and play around with predictive control, because it's so powerful and so much fun. And now we get to the demo. So fingers crossed. All right, let me look at the clock. Yeah, we're good. So let's hit play. So what do you want to try? You want to try the humanoid? Let's try the humanoid. Ooh, that was fast. All right, let's mess with it. I'll do a tracking camera so I can throw it around. Let's take the head. Oh, that was good. Nice. All right, let's zoom out and kind of throw it in the air. Oh, wait, let me grab it by the, oh, nice. Let me grab it by the pelvis. I get more. I don't know, that's just fun. A bit abusive, but all right. And here I can change so now I'm changing the height goal of the head. It doesn't look very comfortable, but it's achieving the goal. Yeah, it often happens if it needs to figure something out, it takes time. Like, for example, let's turn the controls off. So now it's just basically dead. And let's turn it on. It might take it a while to figure out how to stand. Oh, that was a bit too fast. Help me out with the, yeah, you see? So it's like, what do I do? Let's turn on so now I turned on the predictions. So now I can literally see into the mind of the controller. You see how the predicted, yeah, you can literally see when it's about to get up. Yeah? Very visual, very fun. Let's see, what shall we see? You want to see this quadruped on flat terrain? This guy's kind of fun. Oh, it's already in the right place, so it's not doing anything. What am I doing? Ah, here we go. Yeah, I'm changing the heading. I can, here, let's make it go back. Yeah, it's not a very elegant walk, but it gets the job done. It certainly moves. And it is super robust. It's literally difficult to get it to land on its back, because even in the air, it kind of does stuff. All right. Let's go back to the hill demo, because here we have this nice, yeah, wait, let's pause. Tracking camera, go. Because it's a little bit difficult for it to get over that hill. And then I need to slow down. Let's see if it gets over it without any help. Nope. So I slow down the simulation. Now the planner has more time to sample. Let's see if it can do it. Can it do it? Oh, let's slow it down more. Oh, this is a live demo. I'm going to increase the body position cost. So this is another thing I can do. I just increase the cost of reaching the position and it'll do it. Okay, let's speed it up again. Get back to that hill from the other side and see if it can do it with this cost at 100%. I'm honestly curious. I don't know. Oh, yeah, there's a floor there. Yeah, yeah. All right, now it can just do it. All right, let's go to the hand, because that, in some ways, is the most impressive, I think. At least this was the most surprising. What am I doing? Here we go. Now, it can drop it sometimes. It's definitely not perfect. This is not, no performance guarantees, nothing like that. This is the opposite of performance guarantees. This is, try it, it might work, it might not, but it's going to be fun to play with. That's the only thing I can guarantee is fun. I can give you a fun certificate guarantee. All right, let's put it back on this guy. So we have some interesting stuff in the background. And then I think we'll go to questions. Wait, tracking camera. And I think we can go to questions.
When you're doing the planning for
Thanks. When you're doing the planning for the dexterous hand, is it explicitly reasoning about the contact modes when it samples the...
Yeah, I mean, it's rolling out an open loop control sequence. Whatever contacts happen during that rollout, happen. Whatever don't. All it does is roll out, measure the reward, and pick the best rollout.
I see. Thanks.
So in that sense, it's reasoning about it. Like, in as much as it's reasoning about anything, yes. Is it reasoning? I don't think so.
Right, but it is enumerating the modes as it roll out to the nodes.
Yeah. Contacts happen or don't happen, yeah.
Thanks.
Hi, I'm just curious about the decision you made to use finite differencing instead of auto-diffing through some of the dynamics, because wouldn't that introduce bias between the two gradient?
It's a good question. Shall we help this guy out? I don't want this to be a sad affair. I just need to increase this cost, right? That's what we learned. Let's make it a bit slower too. Yeah. So first of all, automatic differentiation is, generally speaking, not what you want in physics simulation. Depends on the algorithm, but generally speaking, almost all physics simulation involve some sort of internal optimization procedure, which is iterative, and you never want to auto-differentiate that. What you want to do is get to the minimum, look at the KKT conditions, and get the analytical derivative from the curvature. And this is something that we can do in MuJoCo, but we just honestly haven't gotten around to it. We have the analytical derivatives of the smooth dynamics, but we don't have the analytical derivatives of the constraint solver. That said, if we did that, this tool would be much less convenient. Finite differencing is so convenient here because if I needed to use analytical derivatives everywhere, I would need to differentiate my residuals. Now they just get auto-differenced by the finite. I'm finite differencing anyway, so just tag something on to the output of the function that you're finite differencing, and you get those Jacobians for free. So finite differencing is very convenient here. Is it slightly inaccurate? Yes, but that's a price I'm willing to pay.
Okay, thank you.
Any more questions?
Thank you. What other computer language does MuJoCo support? Is it only C++?
I mean, we have native Python bindings now. I would not recommend trying to do this in Python, but we have, like I said, we have a Python notebook. Python is great for understanding and for prototyping. If you care about performance, don't use Python. There's also there's Java bindings. There are Swift bindings. Like, since open sourcing, a lot of people have written all sorts of bindings for MuJoCo.
Can I also ask what library do you use to train the neural network here?
There is no neural network.
Ah, okay.
There's no learning.
Okay, okay.
Everything is happening in real time from scratch.
Speaking of learning, so honest questions. I don't know. I haven't tried MuJoCo in some time, but I knew it had some problems with contacts. So I want to know your I want you to comment on. You mentioned transfer learning. I want to know essentially how accurate contacts or in general, like what I'm seeing in simulation, because what I would care about is actually to see things in the robot at the end, right? I can see crazy things and like amazing things in simulation, but I don't know if it's gonna be transferred exactly the same on the robot.
This is a great, yeah. This is a great question. You have another one? I'll get back to it. Wait, let me answer this. Contact phenomena are really, really complicated in the real world. Tiny microscopic things, both in scales of space and time, propagate to the macroscopic arena like that. And people have dedicated their lives to understanding contact and friction. It's very complicated. So all physics engines, including MuJoCo, have only very rough approximations of contact. Now, the more powerful the physics engine is in terms of what kinds of contact phenomena it can simulate, can it do stickiness, bounciness, this kind of slip, that kind of friction, the more power it has, the easier it is for the user to configure it wrong and get something very unphysical. And this is true for any physics engine that has the power to simulate complex contact phenomena. I'm sure it's very true for Drake as well. It's easy to misconfigure things and get bad results. Now, there's two answers to this. One is what they do in the gaming physics engines, which is give you a fixed approximation that kind of looks okay, is completely untunable, but never behaves badly. The other solution, which is the thing that I prefer, is to A, give you good documentation to explain to you how MuJoCo's fairly elaborate contact model works. And the other is ideally, which we will hopefully do this year, give you system identification tools so that you can take data from your real robot and transfer it to the model. And if the SysID tools are good, they will also be able to tell you that I don't really know what your friction parameter is because my model isn't rich enough to describe the kind of friction that I'm seeing in the data. So I have very low certainty about this parameter. And that's what I think all good physics engines that purport to try to describe reality, they should have a way of saying that this thing is not well described. And I hope we will have this in MuJoCo soon.
Yeah, when you mentioned the system ID in the beginning, I thought that would be actually a really great thing to add. The second thing is, so Isaac Jim is, I would say, has been around recently. Before that, like I was using MuJoCo before, way before that. But anyways, like my personal choice now is using Isaac Jim for doing reinforcement or doing learning in general. So can you comment on that? Like, what do you think? Why would I use MuJoCo versus Isaac Jim now, if I wanted to do RL for training?
First of all, if you want to use Isaac Jim, use Isaac Jim. I'll only tell you this. The first time you used MuJoCo, was it via Python?
Yes.
So I can tell you that if you don't use it via Python, it will be orders of magnitude faster than what you experienced last time. And we're also, I don't want to get into it, we're also making like a kind of a C++ layer for environments that will, exploit the threading capabilities of the CPU, and then we'll eventually expose that to Python. So eventually you will have access to fast MuJoCo environments through Python. That will come someday soon. But that's one thing to remember, that MuJoCo was hampered by Python for a long, long time. The other thing that I can say, and this is speculation on my part because the people writing Isaac Jim know what they're doing, GPU code is not pretty. And we are almost completely confident that even though it's probably possible to take MuJoCo to GPU, we don't want to do it because we want to keep the code readable. We want people to be able to contribute. We want to be able to keep it flexible. Like, we love the fact that we can compile for Apple Silicon and x86 and Linux ARM, and we can build for PowerPC. I think we tried once. If you build for GPU, it's what do you have? You have CUDA, and then there are these really hard trade-offs that you need to do when writing for GPU, and I didn't even get to how you need to restructure your code, which is the really bad part. Like, you need to rewrite your code in a way that makes it much more difficult to understand, and we don't want to do that.
Thanks.
All right, I'll ask one question. So I wanted to go back to the metaphor of mountain climbing and surfing. First, just point out the obvious. Mountain climbing, right? If you look right now at the screen, you had to slow down a little bit. Simulation, change it slightly so that it could figure out how to go over that hill. So building on that, what I want to solve is manipulation, right? How far does this metaphor apply to manipulation?
I think it applies most strongly in manipulation, because in manipulation there are so many paths to achieving any kind of task. There's a lovely study made by a scientist from UCSD whose name escapes me right now, where they took videos of people working in factories, and they're doing a repetitive task, like classic kind of conveyor belt type thing. They are doing exactly the same thing again and again and again. If you look carefully at their hands and fingers, they do it differently every time. And that's really fascinating. And I think it's a combination of two things. One is that our muscles are stateful, right? So maybe my right hand is tired, my left hand is achy, but that would explain only a little bit of it. I think the real explanation comes from the huge, like if you actually look at the problem of manipulation, it's this incredibly large combinatorial landscape. And the way to avoid getting into the weeds of the combinatorial problem is to take a machete. That's how you get out of the weeds. Okay, and you can just find this way or that way. And if you actually look at people's hands when they're solving difficult manipulation tasks, they will constantly realign. You know, they don't have a fixed plan. Their hands will just do whatever it takes in order to achieve the task. And I think that robotic manipulation should look similar. It should not plan ahead a fixed sequence of contacts out of the combinatorial expanse of possibilities. It should just forge a path, given the current state. How can I make the situation, the state a bit nearer to the desired state? And I think it's true in manipulation more than anywhere else, because there are so many paths that will take you to the place that you're trying to get.
Thanks. Any more questions? All right. Well, thank you. Great talk.